Let's see how a familiar problem looks using the integral methods we've just learned. So let's say a car is going along a residential street at 11 meters per second. It's braking fairly hard at 6 meters per second, which might not be the same thing we used previously, but let's just use this. And its current position is 60 meters since the most recent stop sign. So let's see, we should graph some stuff, right? So we'll have a of t and t on this axis. And because the car is braking at 6 meters per second, the acceleration should actually be negative. So we'll draw a line here at negative 6 meters per second squared. We also know the velocity is starting here at 11 and heading downward, right? And we'll find out later that it's decreasing linearly, not a big surprise. So what is the velocity at time t? We'd like to know the formula for that graph. I'm actually going to use velocity at time capital T because I'm going to want to use lowercase t for the limits of integration of the integral. So we'll say v at time capital T starts off with whatever initial velocity you have plus the integral little t equals 0 to capital T a of little t dt. Hopefully that looks like the net change theorem to you. And then we can replace this with what? 11 plus integral 0 to capital T of negative 6 dt, which is 11 plus negative 6 little t from 0 to capital T, which is 11 plus negative 6 times capital T minus negative 6 times 0, which altogether is 11 minus 6 capital T. So now we know the form for that function. We can ask, when does this hit 0? When does the car come to a stop? At capital T equals negative 11 over negative 6, or 11 over 6, or 1.833 seconds. So now we know when that time point is. All right, so that's how the velocity is behaving. Now we can do the position. So what is our position as a function of time? So try to write out all the proper calculations here, and then come back. Okay, ready? So we'd say S of capital T is my initial position, plus the integral 0 to capital T v of lowercase t dt, which is 60 plus the integral 0 to capital T of 11 minus 6 lowercase t dt. And then take that integral. The integral of 11 dt is 11t. The integral of negative 6t dt is negative 6 times 1/2 t squared from 0 to capital T. So that is 60 plus 11 times uppercase t minus 6 times 1/2 uppercase t squared minus, and then when you plug in 0 in both parts there, you just get 0 minus 0. So what shape is that? We've got a t squared with a negative on it, so it's an upside down parabola. So we know it starts at, so this is S of t, starts at 60 and increases up to some maximum. And where is that maximum? It would be where the derivative of s is 0, a flat tangent line. Where is the derivative of s 0? Well, the derivative of s, the position, is the velocity, and we know where that's 0. So that's at 1.833. And it hits that maximum in theory, this parabola would continue and decline, but our acceleration would actually drop to 0 at that point because brakes don't actually start pushing you backwards when your velocity is hit 0. So we could then ask, what is this y value? Is it like 65 meters where the kid on the bike is? It ends up being past that, so that means this car had better be braking faster than that, or the parent involved, who we aren't going to name, should train their kid better to not bike into the street suddenly. Or maybe the car should be going slowly if it's on a residential street near something that would obviously have kids running around and possibly not paying attention in the street. I'm remembering now that when we originally posed this question way back at the start of the semester, we said, let's say that the current time is actually 13 rather than 0. So it's a good exercise to go through all that math, and I'll put something like that in the YouTube video description.